We're going to turn our attention now from acids reacting with water and bases reacting with water to acids and bases reacting together. Now, when we have an acid that reacts with a base, and here I've chosen a strong acid and a strong base, we will form water and what's chemically known as a salt. Now keep in mind, this is a double displacement reaction. So I have my H and my OH combining, and then I have my chlorine and sodium combining. So what this is a transfer of the anions or a transfer of the cations, however you prefer to look at it, but it is a double displacement nonetheless. Now, when an acid and a base react together, that's called an acid-base neutralization, because we will form water and, again, what's chemically known as the salt. Now, the salt is comprised of the cation from the base and the anion from the acid. So that is the chemical definition. Now, I chose hydrochloric acid and sodium hydroxide that forms sodium chloride because most people do recognize sodium chloride as table salt. So it's not a big leap to say the salt when we're talking about an acid-base reaction. Now, when a strong acid and a strong base react together, they will typically form a neutral solution when they are in stoichiometrically equivalent amounts. Now, if we had a weak acid and a strong base, we're going to end up forming an equilibrium. So although we're going to have water be produced, then we will also have that sodium anion and the anion, the conjugate base. Now remember from Chemistry 1 that sodium compounds are all soluble. So when I have this salt in water, I'm going to end up making weak acid, and if we've taken a hydrogen away from that water, I'm going to be making hydroxide. Because this salt ends up reacting with water to make hydroxide in solution, a weak acid and a strong base yield a weakly basic solution. If I have a strong acid and a weak base, I'm just going to pick ammonia here, ammonia is a common one, I will form an equilibrium solution. Now the strong acid donates my proton, so I make the conjugate acid, and then I have the conjugate base. Now, the ammonium ion here does react with water. And when it reacts with water, it acts as the acid. So it makes hydronium ions and ammonia. Acid and a weak base, we will end up forming hydronium ions and therefore a weakly acidic solution. Strong acid plus weak base is a weakly acidic solution. Now we can also have a weak acid and a weak base, but that's going to be our most complex situation because we're going to have to view the K's of that situation. So if we have a weak acid, just a generic weak acid, and I have my base, then what I'm going to do is create my conjugate acid and my conjugate base. Then I need to know the Ka's of each of these acids, and whichever one is bigger is where the equilibrium will be dependent upon. So if Ka1 is greater than K, we will produce more products on the Ka1 side and less on the Ka2 side. So we're going to have to see the Ka's in order to judge that. If we have this chemical reaction here, and we have a pH, we're told the pH, no, we're looking for the pH, we're told we start with 0.233 moles or molar of aniline hydrochloride. The aniline hydrochloride is this business right here, and it's a salt. Now we have none of our products. We know we're going to change it some value. So at equilibrium, our concentrations will look like this. So we need to find the Ka of this value so that we can put it into our expression here and come up with a value. Now I don't have an aniline hydrochloride or an aniline weak acid dissociation constant in my table. So I'm going to need to go to the base table in order to find the Kb, and then I'll have to calculate that Ka. So the Kb is 7.4 times 10 to the negative 10. Remember the relationship that the Ka is going to be equal to Kw over Kb. So I'll take 1 times 10 to the negative 14, divide it by the Kb value, 7.4 times 10 to the negative 10, and I get a Ka value equal to 1.4 times 10 to the negative 5. Now these values here, 0.2 and 10 to the negative 5, we are close to not being able to simplify that, but I am going to simplify it, and then I'll check to see if it's a valid simplification. So I'm going to solve for x, and my x value is 0.001, I'm going to round that 1/8, capital M molar. Now I'm just going to do my double check over here. I'm going to take that x value, and I'm actually going to leave it in my calculator, and then divide it by my original concentration, multiply that by 100, and I get a percent value of 0.76%, so that is a valid substitution. I can do that simplification. So this x value here is equal to the hydronium ion concentration. So the pH, remember the pH is the negative log of that hydronium ion concentration. So I have a negative log of 0.0018, and I get a pH is 2.74. For this problem, we are asked to find the acetic acid concentration at equilibrium. We're told what two of the concentrations are at equilibrium. So what we need to do is find, and this is a Kb expression, we need to find the Kb of this compound. So here we have acetic acid and hydroxide ion all over the concentration of our initial acid. So I need to find the Kb of this solution. Now the Kb isn't going to be found in our weak base dissociation stuff because acetic acid is an acid. So what we're going to need to do is find the Ka of acetic acid, 1.75 times 10 to the negative 5. And we're going to need to calculate the Kb. Remember that Kb can be calculated from Ka by taking the Kw and dividing it by the Ka. That will result in the Kb. So I get a Kb value of 5.7. I'll leave it there, 5.7 times 10 to the negative 10. Now I have several of my values and I'm only missing one. So I will put HA for my acid because that's easier for me to keep track of. 2.5 times 10 to the negative 6 divided by 0.050. So when I work that arithmetic, which would be 5.7 times 10 to the negative 10 times the denominator divided by the numerator, and that's just standard algebraic procedure for getting that variable by itself, I get a weak acid concentration of 1.14, so I'm going to call it 1.1 times 10 to the negative 5, capital M molarity. Now, when we're given a salt, we need to determine whether an aqueous solution is going to be acidic, basic, or neutral. If the ions are from strong acids and strong bases, then it's going to be a neutral solution. If the ion is from a weak base, we're going to end up with an acidic solution. If our ion is from a weak acid, we'll end up with a basic solution. So here we have KBr. Well, we're going to put KOH and HBr and decide if those are strong. KOH is a strong base. HBr is on our strong acid list right here. Therefore, since this is both the cation and the anion of strong acids and bases, this would be a neutral solution. For sodium bicarbonate, if we have sodium hydroxide, that's strong, so I'm going to mark it out if it's strong. And then if I have this value, this is a weak acid. So because we have the anion of a weak acid, that would make a basic solution. Here we have ammonium and we have chloride. Well, the chlorine is the conjugate base of a strong acid, hydrochloric acid, so I'm going to mark that out. The ammonium is the conjugate acid of a weak base, and because it's the conjugate acid of a weak base, this would be an acidic solution. Remember how we figure that out. The ammonium ion and water, the ammonium ion would act as the acid, and it would give up that hydrogen ion to the water to form hydronium and ammonia. So because it would form hydronium, it becomes an acidic solution. So number 4, we have sodium, sodium hydroxide. Then I have the conjugate base of a weak acid. So because I have a conjugate base of a weak acid, that makes this a basic solution. And again, just to recap, so I have my HPO4 minus, and I'm going to react that with water. In this case, the water is going to act as an acid, and it's going to give a proton to that phosphate, that's a 2 minus, and then leave hydroxide ions in solution. So it's because of those hydroxide ions in solution that makes a basic solution. And here we have our ammonium, which is the conjugate acid of a weak base, and then we have our fluorine. Going back to our strong acids table, we don't have HF. So in this case, we would have to analyze the Kas. Now the Ka of hydrofluoric acid, so HF, is 6.3 times 10 to the negative 4. I'm going to write that down over here. We're going to need that Kb, however, and then we're going to have our ammonium. And for that, we're going to need to find, that's going to be in the Kb side. And I'm going to need to calculate that Ka. So the Kb is 1.8 times 10 to the negative 5. And I calculate those alternate Ks. And what I have is the Ka of this cation is going to be 5.56 times 10 to the negative 10. And the Kb of this anion is going to be 1.59 times 10 to the negative 11. So because this Ka is greater than this Kb, we would end up with an acidic solution. Hydrated metal ions can also act as weak acids when they are in solution. So we have this hydrated aluminum ion, which is relatively common. And rather than go into all of the inorganic chemistry of that, I want to focus on the acid part. So what's going to happen is, if we're going to calculate this pH, we're going to have this hydrated system. And in water, it will act as an acid. So it's going to give up one of these hydrogens. And when it does that, we only have 5 full water molecules, and then we have an OH. Now, we have a hydronium ion as well. So if we're going to calculate the pH, then we need to treat this as any other weak acid. So initially we have 0.10 molar. We're going to change that concentration by some value x. And then at equilibrium, we'll have these values. Now the Ka was given to us in the text there, and it was 1.4 times 10 to the negative 5. And that's going to be equal to our products concentrations multiplied together divided by our reactant concentration multiplied together. So I'm going to take that 1.4 times 10 to the negative 5. I'm going to simplify this. I don't know if it's appropriate to do so, but I'm going to try it. Multiply it by the denominator, and then I'm going to take the square root of that answer. And I get an x value is 0.00118. Now I can only keep 2 sig figs, so I'm going to call that 0.0012 capital M molar. And that is the concentration of my hydronium ion. Because that is the concentration of my hydronium ion, I can then find the pH as the negative log of that value. And I get a value for pH of 2.9, I'd call that 2.93. Now let's do a double check and make sure that that simplification was appropriate. So I'm going to take my 0.0012 and I'm going to divide it by my initial concentration, 0.1. Then I'm going to multiply that by 100, and the goal is to make that, or to have that be less than 5. And I get 1.2%, so that simplification was just fine.